In this video we're going to take a look at the HackTheBox Console challenge on HackTheBox, and it's an easy Pwn challenge, and the description says check out the all new HackTheBox Console, don't try to Pwn it though. So let's start by downloading the files, or the file, and copy this over to the local directory. And let's do our basic file checks. If you didn't watch the Pwn challenges before this, Reg, Jeeves and Back Computer, I'd recommend watching those first, although I actually found this challenge a bit easier than Back Computer, just personally, but I'm gonna go through this a little bit quicker and not try to demonstrate as much in terms of debugging and different tools and things like that, although we will still go through a lot of the usual stuff. So let's check the file type first of all. It's a 64-bit executable as usual, LSB, ELF, Linux. It's stripped again, just like on Back Computer, so if we do, actually, yeah, let's do strings now. Strings greater than 10, we're not going to have all our function names here. We can see some of the strings, so we've got an idea what the console output's going to be, but we can't see our main function and things like that. So all the symbols have been stripped. Let's see if anything else has been done. We can, for some reason, for me, check sec, I can't do tab autocomplete, but if I do -- file, it'll let me autocomplete, which is kind of annoying. I don't know if that's just a bug with me or what. But right, so no pi enabled. So we had pi enabled last time, meaning that whenever we were setting our breakpoints and things like that, we were trying to find the offset from the base because it was loading at different locations. We don't have to worry about that at this time. The address is going to be fixed, and no execute is enabled this time. So last time our goal was to get some code on the stack and execute it, so even if we can get some code on the stack this time, we're not going to be able to execute it, so that's not the intended solution here. There's no canaries, so we don't need to worry about that. The partial railroad just means that we won't be able to write to parts of the GOT as well, but we don't need to worry about that either for this example. So let's make sure this is executable and try to run it. And we can run it, we can type something in, see what we get, see if we can overflow the buffer. And we're just getting unrecognized commands. So let's go out of this and let's do ltrace and pass it in. And let's do an fgets. So you can see there it's unrecognized command, but we can see that what it was trying to compare our entry with was ID, directory command, flag, half, ls, or date. So if we go back and say ID, it's going to give us this ID. It's printing out using puts. If we do check the directory, it's doing the same. It's giving us directory here. Flag is asking us to put in a flag. We'll say hi. Oh, and it was killed there by the SIG alarm. Alright, cool. Let's open up Ghidra and create a project and go and try and properly reverse engineer this before we open it up in PwnDbg. So create a new project here, and we'll call it console. So we go here and import the file. HackTheBox Console. Okay. Okay. And then double click. And we'll just let it do all its default checks here. And let's see what we've got. So again, the functions are stripped, so we don't have a main function here. We have all the functions been renamed, so we could go through them, try and work out what's going on with those, or we can look for the entry. And we'll see with the entry the function's called here, and this is what we saw where it asked us for a command. So we could have also done that through by looking through the strings there as well. Would have been another good way. So we can see on here that we have a variable declared of 16 bytes chars, and it's whenever we ran the program, let's do it again. This is what we see here, welcome to HackTheBox, and it asks us for a command. Then it's using fgets to take our command. We can do say ls, and it's passing our command to this function, and this function is comparing what we put in. So do we put in ID? It's going to print out this with puts. Do we do a directory listing? It's going to put home HackTheBox. And then we have this flag check, where notice that the flag check, we have a variable here, local variable 16 chars, and then we have this fgets call, which takes in, let's have a look at this, 30 hex. So this is taken in 48 compared to the 16 there. So bear that in mind. And then we have a string comparison here for Hoff, for Hall of Fame, and you can enter a name, and it's going to use fgets, and it's going to put fgets at this location. So there's some data here which is actually going to, it's all empty at the moment, it's actually going to write whatever we put in there. So if we put a name in there, it's going to write it here. So what else do we have? We have the ls, we have the date comparison, where it'll call system date. So what's our attack plan here then? Well, we know where the buffer overflow is. We have this variable, it's 16, and whenever we're writing in here, we're given 48 to write in. So we know we have a way that we can overflow the buffer and put in a new return address. But what return address are we going to want to put in there? We don't have enough room. We don't have enough room to insert a full shell like we did in the last example. You know, that was, what did it come to, like, it's maybe like 45 or 49 bytes or something just for that code. So we don't have enough to do that. And we can't execute code in the stack, actually. I forgot about that. So the no executes enabled. So what can we do? Well, we have this function down here, the system function, which is calling date. So somewhere in memory, we have this system function located, and in fact, the memory addresses, these remain the same. We don't have pi on this time, although that would just enable an offset anyway. As long as there's no ASLR and nothing to deal with here, then we can just use the same. We can just hard code this address, the system address. So we can call system, and then we have this other function here where we were able to write to memory as well. So oh no, the Hall of Fame, where we have the data section here, we're actually able to write to the data section, and we could write something here. So we could write bin/bin/sh, and we could pass it to the system command, or we might be able to write cat flag.txt or something like that and pass it to system. So let's I think that's all the code we really need to look at here. We might keep this open in case we want to grab addresses from here, but there's plenty of other places we can grab those from as well. So let's open up PwnDbg here, GDB PwnDbg, and pass in the file. And if we do info functions here, we're not going to get our functions because it's been stripped, although we can get the address of system. So we can get this and hard code it into our PwnTools script. Although we don't really need to do that, we can also get it from PwnTools as well. But we'll do that first anyway. We'll do it like semi-manually. So if we wanted to get any other addresses, we could open Red from here. We could do AA to analyze functions, and then AFL to list what we've got. You can see we've got this main function here. We can see the addresses of these functions as well. We can also grab system and other addresses from here if we need them. And if we want to do smain and then PDF, go and have a look at the assembly code and again grab more addresses if need be. Okay, but yeah, so we don't really need to do anything else there. If there were any other plugins we want to use, we could type PwnDbg and have a look through some of these, maybe see what ROP gadgets there are, which I think we'll need to do later anyway, or we don't need to, but we will do. Okay, and we need to find the offset as well to our instruction pointer. Let's go back to our Ghidra quickly. We're going to be writing a string here, but we're also going to be overflowing the buffer here so that we can write the return address of the system function and pass in as a parameter the string that we've written to the data section. So we need to find that offset. So let's generate a cyclic pattern, cyclic-l. We could do 100. I'll just do 50 because we know that the oops, sorry, it's not cyclic-l. That's to look for them. We know based on the size of the buffer, it's not going to be much. It's not going to be very big anyway. So that'll do that. So we'll run the program, and we need to do it's flag for this one, isn't it? Flag. We'll paste that in. Let's crash the program as it should. And because it's 64-bit, we don't see our instruction pointer, the RIP, filled with the pattern. So we just take the first 4 bytes of from the RSP, which would have made it into the RIP, or the instruction pointer if it was a 32-bit program. We can do cyclic-l to look up the offset. Cyclic-l, and then we'll see that it's 24 bytes in. So whenever we're writing our script and we're sending to this, using that flag command, we're going to need to send 24 bytes plus the address of the system call, and then plus the parameter as well. Let me actually just show quickly gdb-peda, gdb-peda, because I like the way it did the pattern create. Let me do pattern create 50, same as we did there. See, it uses a different style of pattern here. And I'm going to do run. I'm going to do flag. I'm going to paste that in. It's going to crash. And then I'm going to do pattern search. And it tells us it's 24 bytes in for our RSP, which should be our instruction pointer. But it also tells us as well how much space we have. So we can write 23. We can write our instruction pointer, and then we've also got 23 bytes after that to put our parameters and things like that. So I mean, you can do that in PwnDbg. I just really like the way Peda did that, and I quite like some of this format as well. But I'm getting used to PwnDbg. But if you use Peda, I don't know, you're lucky to have that cool pattern searching. Alright, so we've got the offset. We're gonna, as usual, find that in our PwnTools script anyway. But let's do something else. Let's have a look at where we want to write our data to memory or string. So this one was the Hall of Fame. If we run it again, do Hall of Fame, it asks us to enter a name. Let's say our name is bin/sh, and it says see you soon. So if I hit Control and C here, it'll jump out, pause the program execution, jump out to a stack. And what we want to have a look at is, let's go back to Ghidra. And in Ghidra, it was fgets, and the fgets was to this data location. And the data location is right here. So let's have a look. Let's copy that. And let's do x over x8 and paste that in. 0x. Cannot access memory address. Okay, let's. Oh, x over 8x. What am I doing? Okay. X over 8x. Alright, and let's view it as a string, and there we can see we have our bin/sh. So as expected at this location, it's written our data, and we would have room for more as well. Data to put there, so we could put something else. We could say cat flag.txt. We could be putting code to execute, seeing as this is actually being written as data. But anyway, we've tested that out. We've made sure that works okay. We've got our addresses now, so we know what the address of the function, of the system function is. We know what the address of the location we're going to write the string to is. We know what the offset of that we need to write to overflow the buffer and get the return address. So we have everything we need to go and craft an exploit. Let's open up PwnTools and start putting together a script. Let me copy the template across, and we'll call it console.py. And let's open that up. There's a couple of scripts I'm going to put together for this. One will kind of do things manually, and then one where we'll try to use ROP objects to try and automate some of the stuff for us, but we'll do things manually to begin with. So we need to put in the binary name, just update this template, and it's HackTheBox -console, HTB console. This, as usual, this is going to grab the context for us, so we don't need to worry about what operating system it is, what bits, the architecture, anything like that. And we want to find our offset first of all. Although we know it's 24, and we could just type in 24 very easily, why not begin by finding our offset? Why not? So we can pass cyclic 100 to this function, which is already set up for us here. Because we're dealing with 64-bit, we're going to go and comment that and uncomment this because we want to read from the stack pointer instead of the program counter, because as we saw, it was not going to load the pattern into the instruction pointer because it's an invalid pattern. Okay, and what do we need to do to crash the program? Let's run this again. HackTheBox console. It comes up with a --, and then we need to put in the flag, and then we put in a long flag here. So let's after --, let's take a copy of this. After --, we're gonna say flag, and then it's gonna say enter a flag. So after it says that, we're gonna give it 100 bytes of this cyclic pattern. We're going to wait for the program to crash. We're going to read the core dump and find the offset of our pattern, and we're going to return that. And let's set this to debug as well, and just get some nice feedback as we run it. So we'll do Python console. So it's running through, and you can see here it's located the offset at 24 as it should. You can see what it sent there, the cyclic pattern that it sent, and everything as it happened. If we go and set that back to info, it can be a little bit noisy. And this time we pretty much just get our offset. Alright, so now that we've got our offset, that's out of the way, let's go and uncomment some of this code and start to work on it. Let's uncomment this. We'll start the program. Again, as usual, we can pass in GDB in capital letters if we want to launch GDB. We can set up the script here, set up our breakpoints and things like that. Or we can pass in remote in capital letters and pass in a server and a port separated by a space, and that'll do it all remotely. If not, it's just going to run locally for us. Okay, so let's set up some of the addresses here. We have a system address equals, and we can get that from Ghidra, or we can get it from, let's if we disassemble, disassemble system. Do we have our system? Yep, system at PLT. Okay, run. Disassemble system at PLT. Let's, okay, we don't need to do that anyway. Let's just do, open up Red Air, we'll do AA, AFL, S. Oh, we don't even need to do, we've got our system thing here. Okay, we'll just grab that and paste this in here. You can take the zeros out of it as long as we've got a context set here to 64 bits. It'll worry about the address sizes for us here. If you're not using flat to flatten it, you might need to just use pack. But then again, you need the context set. So if you don't have the context set, you'd need to say P64 or P32. But we've set all our contexts and things like that, so nothing to worry about. So let's also get the address of the string. That's what we wanted. It's right here. This is going to be our bin/sh string that we're going to write to memory. So we'll say this is bin sh address and paste that in there. What I will mention as well, in fact I'll comment this out, the address of system, and just show that another way we could have done this, an easier way really, would be to say elf dot elf.symbols, sorry, what am I doing? elf.symbols.system. Or you can do like this. And just to demo what we have there, let's actually, we'll run that, but let's print out elf.symbols. Okay. Pretty print. Okay, we'll run that console, and you can see it's printing out here. It's printing out all the different functions and the GOT and the PLT procedure linkage table, the global offset table, and it's giving us the addresses in ints. So we don't need to go and find these things manually. We can find them from there. We can also search for strings in memory and things as well. So we can automate this this whole process, but it's good to go through and do it manually as well, so you understand what's going on and how to use some of the tools to do it manually. Okay, so with that done, let's take out this print statement, and one other thing that we're going to need to do is get a ROP gadget. So we're going to need to pop RDI because it's 64-bit. The calling convention is that if we want to call the system function, we first have to pop the parameter that we want to pass to system. So if we want to call system bin/sh, we first need to pop the bin/sh string into the RDI register from the stack, and then we need to call the system function, and then it'll use that parameter. So we need to go and find that. We could actually find that again through PwnTools by doing a ROP gadget search, but let's go and do it manually. So we can use ropper here. Let's do ropper-f. You can use ROP gadget as well as plenty of tools, and you can also do this from inside PwnDbg. But we'll do ropper-f, pass it to the HackTheBox console, and we can do that. It'll give us all the ROP gadgets and their addresses. We can also then say --search and say we want to search for pop RDI, and it'll find that gadget for us if it exists. We can also, if we don't want to search, we can say we want to go into console mode, And then from here, if you hit tab, you'll get a list of different things we can do. So if we do ROP chain, let's see what we can say. We want a ROP chain, for example, ROP chain exec ve, and okay, saying cannot create. Maybe I need to provide more stuff here, but we can, if there's we can look for stack pivots. If there's any gadgets here for doing stack pivots, things like that. We can do our searches, Oxcodes. There's a lot of things to do there. Let's just grab our pop RDI address, and that'll do us for now. So pop RDI is equal to 0x, and we've got that address as well. Okay, so we need to build our payload then. Let's remove the comments from this. I'm going to remove this write payload because it's not the kind of challenge we'll just be able to write a payload file for easy replay on. And what's happening here is we can give to flat. If we highlight that, it should give us some info about it. Oh god, this. And it says this function takes an arbitrary number of arbitrarily nested lists, tuples, dictionaries. It will find every string and number inside those and flatten them out. Strings are inserted directly while numbers are packed using the pack function. Unicode strings or UTF-8 encoded. So because we've got a context set, it's going to do all the flattening and things like that for us. And we could just say at the offset that we've identified here, we want to put in our system call. Essentially, this is kind of what we are going to do. But instead of just passing in a string, we're going to give it an array, and then the array that we're going to pass to it, we need to call the system function, obviously, so we'll give it the system address. But before we call the system function, we need to pop our bin/sh address into the RDI. So if we do a pop RDI gadget, which we've got the address of here, and then we do our bin/sh address, which we've got here, and then so what's going to happen is this is going to pop the next thing that's on the stack, which is a bin/sh address. It's going to pop that into the RDI register, and then it's going to call the system function, and the system function is going to go to the RDI register and say, give me whatever parameter you've got in there, and the parameter will be our bin/sh string. So I think that's all good. What we need to now do is actually write the bin/sh string to our data section. So what do we need to do here? Let's grab our we can use the same code that we had up here to send the request off. Just change this to IO. Oh. And instead of flag, it was HOF for Hall of Fame. And let's actually run it to see what the prompt is. HOF, enter your name. So we'll grab that and put that in there. Enter your name, and the name that we're going to enter is going to be bin/sh, and that should write that to this address, which is the address that we're going to pass as a parameter to the system function, which is going to call bin/sh, which is hopefully going to get us the flag. So now we just need to do the overflow as well. Let's grab this. It's going to be the exact same code. It's right here for send the payload. And yeah, we don't need to change anything at all there. That's fine. All we need now is to say IO interactive. And this should be us getting a shell. Let's test this out. So we'll run Python console.py. We get p is not defined because I forgot to change this. IO. Oops, wrong flag. That's fine. We were expecting it to come up and say that because we entered that flag in. But look what we have here. Look, is this a shell? It is a shell. So that's cool. We've got a shell. Now let's test this out remotely and see if it works. So we'll start the instance here. Remember, this is nice and easy for us because we can do python console.py remote in capital letters, and then all we need is the server address and port number. And if we try to run that, oops, got the wrong flag, but if we say ID, see that we're root. If we list the directory, we'll see that we've got a flag.txt here. So we can cat that out, flag.txt, and boom, we have the flag. So yep, nice and easy. We could go through and set that to debug if we wanted to go through and get a good analysis and try and break down what's happening as we go and see our shellcode as it's being sent here. Yeah, so also we have this here, it's called flag.txt, so let's see if we can get it to print out a flag, just cat out flag.txt. Now if I put here, let's go bin sh, let's try cat flag.txt. I'm going to try this locally. I'm going to set up a local flag again. Let's do subble flag.txt flag fake flag. Sure, I had that as flag.txt there, but okay. Save that and so this time we'll be wanting to do this flag receive instead of IO interactive. The only thing is that we also need to be aware that we had the whoops wrong flag message, so let's let me run that again locally. See this, we get whoops wrong flag. So we can say io.receive until, and then paste that in as well, and then the new line so that it'll just go straight to our flag. Let's try that out. And you'll see that we get this cat flag no such file or directory. If we try though to cat flag, let's try that, and that works. Let's try that remotely, and that works as well. Okay, cool. One other thing I'm going to do is just go through and demo this using a ROP objects as well. So I'm gonna leave two scripts on my GitHub. I'll leave this one with a lot of commenting on it, which is not on here yet, and I will, but it will be to get a reverse shell, and then I'll leave the ROP one that we're about to create as well, which will be to cat the flag.txt instead. So yeah, let's see what we could do here. We could take away a lot of this stuff. We don't really need to find this pop RDI gadget, so let's take that away. We don't actually need to even call this system. Here we can get that with ROP objects. So let me do this before we send this off. Oh, we can do it after. So we'll send this off. It's still just the same. We're going to be cat flag, but now we're going to say we're going to take away our array here, and at the offset, instead of passing in that array where we needed to pop this value into the RDI, instead what we're going to do is we're going to create a ROP object. I'm going to say ROP equals ROP with elf as a parameter. And then we're going to do ropper.system, and we're going to pass in as a parameter the bin sh address, and that's basically it. We can just pass in now here rop.chain. Let's have a look, And if we try to run this locally, we get our flag. Try to run it against the server, we also get our flag, and you can see it's done the command just the same. So the cool thing is, yeah, that we this ROP chain, we can let's actually print that out, the ROP chain here. So let's do print rop.dump. Let's have a look at that. I'm going to change this back to info. Okay, and you can actually see that the ROP chain that it created there is pop RDI return, where it pops to the RDI the bin sh address, the string, and then it calls the system function. So it does everything that we did last time, but it just put that all together for us because it was able to resolve the system function from this elf binary. We can also, if we want to have a look at, if we wanted to have a look at the gadgets here, we could say pretty print rop dot gadgets. Let's do this locally, and you can see the gadgets that are available to us. We could be searching through gadgets as well in there rather than going to find them manually, etc. Yeah, so alright, I'll put both of these, I'll put two scripts on GitHub, and I hope you've enjoyed this video. If you've got any questions, comments, you can leave them down below. Thanks.